Hello everyone. This is a video lecture for Calculus 1, section 3.10, linear approximation. They have a formula for you. L of x is equal to of a plus f prime of a times x minus. And I go and use this throughout my whole notes. Every single time I reference this, I do go back to this formula and stuff. I'm going to do a whole different thing. I'm not going to do this. I'm just not going to do it. Instead, I just want to try something else. I'm going to try y minus y1 is equal to m times x minus x1. Notice that this right here would have been on this side. This is a y value. This is my slope. This is an x value. So, I mean, that's all we're doing here. So what they did was they took this to the other side and just added it. I don't know. You can put it in the back or the front or wherever. Because it's a line. L stands for line, linear line. Do you see it? But not just that, but see where we have a derivative here for my slope. So this is a tangent line. Yes, every time we're going to be doing a tangent line. And so that's really what's going on here. Is that at some point we got a tangent line going on, and there we go. Now, why? Why are they calling this linear approximation? Well, basically, what if I want a point like right here at the tangent? Well, we've already found it. But what if I got a point that's somewhere nearby? And so let me zoom in on this, okay? Let me just zoom in. Let's say that I have this graph, and I have my tangent line. I'm trying the best I can here. And I want a point right here. I want to find what's the y value. Well, it's pretty close to the tangent line. I know this is the actual point that the tangent line is on, but it's approximately the same. And so if we got a really close value, we could use the tangent line to find out the approximation. Now, you might be wondering, why don't we just plug it into the original to find the actual value? Because lines are very simple to plug things into. Crazy, huge, long polynomial things are not. And maybe we have the derivative not because we took a derivative, but because somehow we calculated it. I would say, if anything, this is the most engineering-focused section. Not just because it's applicable, but because you're taking real-world numbers and you're doing the best you can, okay? You won't get perfect, and that is okay because, you're putting up a house and some of the studs are not perfectly the same length. It's going to be okay. It's going to be okay. The whole house will not fall down because of a couple millimeters, okay? So, that is the point. So, as my notes go, I'm not going with my notes. I'm just going to do tangent lines. And I just decided that a minute ago. Because I said, well, why not? So this is what they give me. And so what I need to do is find the tangent line at 16. And so, first off, what is my derivative? Well, derivative would be 1/2 x to the negative 1/2. That's pretty easy. I guess if you want to make it pretty, you could do this right here. This is my x value, and so what I'm going to try to find is my y1. So my x1 right now is 16, by the way. Y1 is when I plug it into this guy, so the square root of 16 is going to be a 4. But then I want to find my m, and that would be plugging it into my derivative. And so that would be the 1 over 2 times square root of 16. 2 times 4 is 8, so 1/8. So I got my x1, my y1, and my m. And so then y minus y1, m x minus x1. And so then I got a 4 here. Sorry that my y's and my 4's look kind of similar. 1/8 x minus 16. Move the 4 over and you're done. And so what I did right here, I'm going to leave it just like this because that is the linear approximation in their format. This is that f of a, f prime of a, da-da-da. Whatever. So there you go. If we need to use it or even simplify down more, that's fine, but it's just a line. Okay, so I got a fifth root of 1 plus x, and they're saying we have a is equal to 0. Again, that's my x1 is equal to 0. And so I need to find my derivative first. Derivative is going to be a 1/5 comes to the front because this is a 1/5 power. Leave the inside alone, and then minus 1 in front of the power makes it a negative 4/5. I know this inside is complicated, but when you take the derivative of it, it's just going to be a 1, so that doesn't really change anything, thankfully, there. So let's try to find some stuff now. My x1 is a 0. My y1 is when I plug a 0 into here, so the 5th root of 1 plus 0. The 5th root of 1 is just a 1. And then my m is when I plug it into this guy, which is looking weird, I know, but we can do this. Plugging in a 0, 1 to any powers itself, so it's just 1, 1/5, there you go. So we should be able to do y minus 1 is equal to 1/5 x minus 0. Move it over, and so your answer is 1/5 x plus 1, and there we go. All right, pause. I have something in my notes here where apparently I got angry. I got angry because I'm like writing stuff out and I'm trying something and it didn't work and I got capital letters all over the place, and then I scratched through the whole thing because apparently I was misunderstanding what they were looking for. This is your part A answer, and now part B is going to ask for, well, now find the 5th root of 0.95. And you know what? If you plug this into a calculator, you will get the right answer, but it will be wrong in WebAssign. Isn't that annoying? Okay, so we need to use what we just found for this and this for this. Well, let's compare with my original. I got the 5th root of 1 plus x. Should somehow equal the 5th root of 0.95. What's going on here is that we're actually saying this is 1 minus a 0.05. Do you see it? And so in a way here, I'm saying that my x is equal to a negative 0.05. Okay? Now that I take that, I can plug it in here. 1/5 times the negative 0.05 plus 1. I plug them in, and I get 0.990. Hold on. 990. There we go. Okay. And then they say do it again for 1.1. Well, what this is 1 plus 0.1. Therefore, x is equal to 0.1. I can plug that in. 1/5 times the 0.1 plus 1, 1.020 is what the answer is. So what they're trying to say is compare it to the original, see what my x is, plug it into my answer for part A, plug it into the line, and that way we can get our linear approximation. Okay, f of x is equal to sine x, and a is equal to pi over 6. Again, this is my x value. So, okay, let's find my derivative. Super easy as cosine. And so then my x1 is pi over 6. My y1 is sine of pi over 6, which is the smaller of the two as a half. And then my slope is the cosine of pi over 6, which is the bigger one, square root 3 over 2. So y minus a half is equal to square root 3 over 2 x minus pi over 6. Move this guy over, of course, and that will be your answer exactly as they normally have it. Just copy this thing down. Okay. All of these are actually saying, oh, well, guess L of x. Great. L stands for line. Linear line. Okay. 3, 10, 0, 0, 9. I've got y is equal to tangent of the square root of 5t. And they say find dy. Now, we did this. Do you remember when I changed my y's into dy's back in the implicit section? Those were my flags. I showed you this method. And so, not that we always use it every time, But here they're trying to use it, and that's what we're going to do for them because they want to do this. Fine. D stands for derivative. Or you could just have said this is y prime, basically. Not really, but that's basically what's going on. Okay, so derivative tangent. Do you remember that one? It's secant squared. And then you take the derivative of the inside. So that's a 1/2 power. Now it's a negative 1/2. Take the derivative again. Get a 5. All right. Whoa, that got complicated real fast. Now here's the last thing. Did you forget it? dt. Because you took a derivative with t's. You're doing your flag. It's your flag. That's all. You do not need to simplify, but if you want to, that's fine. So I got 5/2. Actually, that's going to be a square root in the bottom, so let me do this. 5 over 2 square root of 5t, and then times the secant squared of the square root of 5t. dt. Definitely got to include the dt. Include the dt. Otherwise, it's going to say, no, you're wrong. And that's really annoying to hear. That's part A. So part B now says we have this new, I can't remember if it's a part A, part B, but I have continued. And apparently I don't know, I didn't do anything else. So I didn't put a new number. It must be the same problem. Just, figure out something like that again. What they're going to want here in this case is blah, 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 dv. Okay, so my dy is going to be derivative of this guy now. Low d high minus high d low divided by the square of what's below, dv. And you are done. You can, of course, simplify. What happens is that this negative 2v and positive 2v, what's going to happen is that this negative is also going to be there. And I think everything cancels here with those guys in particular. But they're going to combine with these to make a negative 4v over all this stuff. Oops. Okay. And then dv. Must include the dv. Otherwise, they're going to say you're wrong. All right, y is equal to e to the x over 4. So y prime, oh, my bad, dy is equal to 1/4 e to the x over 4 dx. And you got to include the dx. Otherwise, they're going to say you're wrong. All right, and then that's part A. Part B says x equals 0 and dx is equal to a positive 0.01. And so then what's your dy? So yeah, guess what? You just plug them in. And so then we got e to the 0 is a 1, 1/4. 1/4 of that guy is going to be a 0.025. And there we go. We plugged it in. 310.023. I got y is equal to x squared minus 6x. X is equal to 5. And delta x, have you seen that? Delta x equals 0.5. So what are they trying to say with delta x? On top of that, they say delta y is equal to what? And then they say dy is equal to what? And they're apparently different. So this is a manual approach, and this here is a calculus approach. Because we've been doing calculus so much, let's just do the calculus one right now. Calculus is 2x minus 6, again dx. Thankfully, dx and delta x are actually the same thing. So my dy would then be 2 times 5, 2 times 5 minus the 6 times 0.5. 10 minus 6 is a 4. 4 times a half is 2. Turn the page and make sure. 2. And this is because, again, my delta x and dx are actually equal. Always. Why is that? Well, because they're independent variables. And already that that should give you a lot of that's all it is. It's just because they're independent variables. But because I said that, that leads us all into a huge other discussion, and I'm not going to go down that road. Just go back to your algebra understandings. We've got independent and dependent variables. Independent, they're the same. There you go. All right, so let's talk about doing this manual method now, because, like, what do I do? So I got delta y is equal to what? Well, what's going on is that this is a y2 minus a y1. I'm doing the difference between two different y values. And so I have what my y's should be, and I'm going to plug in a 5, and then I got this guy. But notice that my 5, I'm increasing it by 0.5. 5 plus 0.5 is 5.5. This is basically like an x2, and this is like an x1, okay? And so let me write those out. So I got my x2 is a 5.5. I got an x1 is just a 5. Now, I'm not wanting to do slope. I know you're saying, oh, y2 minus y1, x's and stuff. No. This is my answer. This is it. Don't do anything else. Don't divide it. But we have to plug them in to find out what's going on. So y is x squared minus the 6x. And so I'm going to say y2 would be 5.5 squared minus 6 times the 5.5. Ugh, that is just the ugliest. Gross. Okay. Definitely calculator, and I got a negative 2.75. My y1, I'm going to plug in a 5, which is a little bit more integer, and I got a negative 5. And so if I take y2 minus y1 manually here, I would get negative 2.75 minus a negative 5. Two negatives make a positive, obviously. And we end up with 2.25 as my delta y, okay? So let's give some formulas. dy is equal to blah, blah, blah dx, okay? Delta y is equal to y2 minus y1, and delta x is equal to dx, which we can plug in up there later, okay? So this is the only calculus that you're doing. Everything else is just manual geometry, algebra, whatever you want to call it stuff. All right, this is actually the very last problem, and we're so close. But of course, it's a word problem. It's got a ton of stuff. So the edge of a cube is 15 centimeters, and it says that there is an error in its calculation by 0.2 centimeters. So I'm measuring the thing, but my ruler is not a perfect ruler. It's not... You know, as I'm measuring out 15 centimeters, it could be off by a little bit because it's a ruler. Okay, so anyways, use differentials. What is that? Use differentials to find the max possible error. Max possible error. Okay. Well, let's start with the volume of a cube. And so I'm just going to go ahead and tell you volume is equal to x squared. No, sorry. X cubed. Cubed. Sorry, that was totally a stupid mistake. Yeah. X cubed is my area because, again, it's all the same sides. All the sides are the same. You're thinking, oh, but it could have a different side. No. This is literally cube. It's a literal cube. So they're all the same. And so what I'm going to find right now is I'm going to find the derivative. So dv is going to be equal to 3x squared dx. There's my flags and all that kind of stuff. And let's try to understand how this works, okay? So what I need now is I'm going to plug in what we got. So first off, my v itself is going to be 15 cubed, which is a 3375. Okay, awesome. And then my dv is going to be equal to 3 times that 15 squared, and dx is this guy, so 0.2, positive 0.2, and it ends up being a 135 centimeters cubed. So that's my dv, okay? And then I'm going to divide those two numbers by one another to get 0.04, which is strange. And that ends up, if you look at it percentage-wise, it's 4.0%. Okay, now what did I do and why did I do it? Are we okay with finding the volume? Yes. Can I just find the derivative and plug in stuff wherever I need it? Yes. Could I divide these two? Yes, but what do you mean here? So let's go back to what they're actually asking, because they actually have 3 boxes. They say the max possible error, and then they go blank centimeters cubed. Right there, the 135. Okay. Let me actually just use a different color for that. 135. Okay, so what else are they asking for? They say, what's the relative error? And they go blank. That's it. Well, relative means in respect to the maximum and all that kind of stuff, the actual volume, the actual value. And so we got the 0.04 here, and that's why I'm dividing them. Let me explain that more in just a second, but let me just finish this guy up. And then it says, what's the percentage error? And they actually go blank percentage. And so they're just taking the same value that we had, and we're changing it into 4.0% because you shift the decimal twice. So let's just say that we had this little box cube thing, and it's 15 centimeters all over the place, right? And it's off by 0.2 centimeters. And so it could be shaved off or a little higher, and it could be on this side a little bit and here, and it could be a little longer, and it could also be a little shorter. So what I'm getting at, there's a lot of different variables that go on. I could have 15 times 15.2 times 15.2 times 15.2. You know, I'm just curious, what is that number? So 15.2 times 15.2 times 15.2, and I've got 3511.808. Okay, interesting. And so if I, but the rate. Anyways, what I'm saying is that my original was the 3375, and now we have 35 whatever it is going on there. I'm curious. Let me just see right quick. What if I divide those? So 3375 divided by 3511.808, and I got 96. I got 96%, which is the opposite of my 4%. So in a way here, you could do it manually like that, I guess. I don't really know. That's not really what I would be doing personally. But I'm saying that the sides can all be changing, and I'm wanting to know what is the relative error. So what if we had a super huge, right? Let's just not say it's 15 centimeters. Let's say this 15 meters. Super huge. And then I'm saying, well, it could be off by a little bit. It could be off by 0.2 centimeters. I mean, that is so tiny in comparison to this thing. Let's just say it's 15 kilometers. Like space cube. This is so huge. It's like a city in space. And it's off by 0.2 centimeters. Relatively, that doesn't mean a lot. Okay? 0.2 centimeters is very tiny compared to 15 kilometers. And so that's what they're really asking for is, what's this relative error? So that's why we divide them out to see about what it would be. So if it were kilometers, it'd be something crazy like this, right? And you would see you get a very tiny number because the percentage would be so tiny it wouldn't really matter much. So there we go. And now I'm done. And that's all I got. Thank you very much, and have a great day.